Okay, in this video, we're going to talk about something called the heat equation or heat conduction equation. And we are going to give the differential equations for it and then state the solution and then do a practice problem with it. We're not going to really explain where the formula comes from or where the equations come from. We're just going to sort of take it for granted and then just apply those facts to a few sample problems. And a reference for this is the book by Nagel, Saff, and Snyder, Fundamentals of Differential Equations, section 10.2. And there's also chapter 10 in Boyce and DePrima, the book on differential equations. Actually, in the Boyce and DePrima book, the old editions start out talking about the partial differential equations, and in the newer editions, they leave the partial differential equations to a later section. So I'm just going to say chapter 10 because that's where the section is, that's where the material is in. So now we're talking about partial differential equations. These are differential equations that involve partial derivatives. And so these are different from ordinary differential equations, which do not involve partial derivatives. And partial differential equations are important in physics and engineering and things like that. So one example of this is something called the heat equation or heat conduction equation. So what is that? So pretend that you have some sort of rod or bar, and assume that so it's heated. So at each point, let's say this is x equals 0 and this is x equals L. So L is the length of the bar. So assume that at each x, the bar is some temperature. And in reality, the bar is three-dimensional, but let's just assume that this is a really thin bar, so the temperature is the same at each x, right? So in reality, I mean, you're going to have something like this. And it's, possible that at x equals, this value, okay, you have this cross-section, and maybe in this cross-section, the temperature is different depending on which point you're at. We're not going to worry about that. We're just going to assume that it's the same temperature at each point in the cross-section. So let's just go back to what we had before. So we're just basically pretending that the bar is a line. So you have this bar, and it goes from 0 to L, which is the length of the bar. And let's say that the temperature is called U. Now, it's not just dependent on the position x you're in, it's also dependent on the time, because basically the temperature of this bar is going to change over time, right? So U of xt is the temperature of the bar at position x and time t. So, I don't know, x is somewhere between 0 and L, right? And let's assume, for simplicity, that the temperature at the ends are 0. So that would mean that U of 0t is equal to 0, and U of L of nt is equal to 0 for all t, say greater than 0. Okay? And also equals 0. So basically, we're assuming that the bar is always 0 degrees at the ends forever, right? It's never not going to be 0 degrees at the ends. It's always 0 degrees at the ends. Okay, well, the temperature over time is going to depend on what the temperature distribution is at time 0, right? So we have to know what the temperature is at time 0. Oops, No. We have to know what the temperature is at time 0, and that's going to be u of x comma 0, right? Now, that we will talk about later. So this will be, in general, this will be some function of x. This would be the temperature at time 0. Do you see where the partial derivatives are going to come in? Because the temperature is a function both of x and t, right? It has two independent variables. X is the position and t is the time. So you have two independent variables. When you have a function of two variables, like temperature in this case, it's going to have partial derivatives. So you're going to have partial differential equations. Okay. And what is the differential equation that is satisfied by the temperature? So it turns out that there's a useful description of this that people in physics or whatever discovered, and I'm just going to write down the formula and let's just not worry about where it comes from, but let's just accept it. The equation for the heat flow is partial u partial t. So this is the partial derivative with respect to time. Well, when you take a function of x and t and take the partial derivative with respect to t, the result is also a function of x and t. So this is going to be a function of x and t. So I'm using, this is the function notation, right? This is going to be some constant, which is positive, times the second partial derivative of u with respect to x. So remember that that's written like this. So this is a function of x and t, okay? And beta is some constant. So yeah, so those are the equations that you have, okay? So let's call this, no, do I have a notation for this? Let's see. Yeah, let's call this equation 1, let's call that equation 2, let's call that equation 3. So let's just review what's going on. So equation 1 is just a formula that was figured out by physics people that describes the flow of heat, the temperature. And then the second equation just tells you that at the ends, the temperature is always 0. And then the third equation just tells you that at time 0, the temperature is whatever it is at x, so f of x. So your f of x is going to depend, right? So if you wanted a constant initial temperature, like everywhere in the bar it's the same temperature, then your f of x would be like 10. But if you wanted the temperature to start out not the same at each x, so maybe your f of x is like x or something. So that would mean, if your f of x was x, then that would mean that at x equals 0, it's 0 degrees, and then at the end, it's L degrees, right? So, I mean, the solution to the differential equation is going to depend on what f of x is. So, okay, so this is the equation for heat flow. So this is sometimes called the heat equation or heat conduction equation. And this constant beta is a positive constant called the thermal diffusivity. And it depends on various aspects of the bar. So it depends on something called the conductivity, and it depends on the density, and some other physical things. The heat of the material in the bar. Okay, and it turns out that this thermal diffusivity depends on the material. So for silver, it turns out to be 1.71 centimeter squared per second, or is that? No, S is not second. It's some sort of version of heat. I don't know. I'm not a physics person. So the point is that it's some number, and the number depends on the material. Okay, you don't need to know any of that for this class. For this, you just need to know that there is some constant that's like 1 or 0.6 or whatever. It doesn't actually matter. So it's some number. Okay, so you have these three equations that tell you the temperature at time t and at position x. So I'm just going to write down the formula for u of xt, and this is the solution to, I'm going to solve 1 and 2. So without 3, not 3, the solution to the two equations 1 and 2. So if you wanted to find all the functions that satisfied equations 1 and 2, it turns out to be u of xt equals the sum from n equals 1 to infinity of some constant c sub n times e to the negative beta n pi over L squared t times sine of n pi x over L, where Cn is any constant. So the math lingo for this is an arbitrary constant. That means that the Cn's can be any real number. So let's put this in a box. So this is solution to 1 and 2. So we're forgetting about equation 3 for now. Okay? This is the general solution to the boundary value problem given by equations 1 and 2. So in the references that I give, they actually explain how you get this formula. It uses something called separation of variables. It's this technique to solve partial differential equations. But in this video, we're not going to go over where this formula comes from. We're just going to accept that it's just true. And we're going to apply it. So where does the third equation, u of x0 equals f of x, come in? So that is used to actually figure out what the Cn's are. And the Cn's are going to depend on your f of x. So basically, if you just care about equations 1 and 2, okay, then the solution is what I just wrote down, and the Cn's can be any constant. But if you impose the third condition that your u of x0 is f of x, or you specify your f of x, then that's going to determine the Cn's, right? Your Cn's can't be anything in that case, because they're going to depend on your f of x. So here's an example. So solve, oh, by the way, let's just remind ourselves that another notation for the partial derivative with respect to t is just u sub t. It's a lot faster to write that down. And then if you want the second derivative, like if you want the partial derivative with respect to x, the second partial derivative, you would do u sub xx. Okay, so sometimes it's written as u sub t equals beta times u sub xx. Also in the Nagel, in the Boyce and DePrima book, instead of beta, they use alpha squared. Okay, in the Nagel, Saff, and Snyder book, they use beta. So anyway, solve u sub t equals 7 u sub xx. So I'm just using this notation because it's faster to write down than the partial derivatives, the d's. So from 0 to pi, x goes from 0 to pi, and t is greater than 0. U of 0t equals u of pi t equals 0. Okay, well, that's not that bad because we just have to figure out, so that's the question, we just have to figure out L and beta. Well, they basically tell you what L and beta are. So L is pi and beta is 7. And so by the equation, u of xt, we just substitute 7 and pi. So we get the sum from n equals 1 to infinity of Cn e to the minus 7. And then you get n pi over pi, right, because L is pi. So you get n squared t. And then sine, then L is pi, the pi's cancel, nx. And that's the answer. Okay, so if they just, so for this question, that's the answer. Now let's do one that's more complicated. So it's the same thing. Solve u sub t equals 7uxx. X goes from 0 to pi. T is positive. And then u of 0t equals u of pi t equals 0. And also, now they tell you that u of x0 equals 3 sine 2x minus 6 sine 5x. So that's your f of x that they're telling you, right? So this u of x0 again is the temperature at position x at time 0, right? That's this 0 here is telling you that you're at time 0. So this is the initial distribution of the temperature. All right, well, that's still not that bad because we have this u of xt from before, but now, okay, we're going to plug in t equals 0. So you have this u of xt. Should I just rewrite it? Fine, I'll write it all over again. So this u of xt came from these two equations, right? Those two, the first two. You get the sum from n equals 1 to infinity, cn e to the minus 7n squared t sine nx. So if we only cared about the first two equations, the cn's can be any constant you want. They can be positive, any real number, positive, negative, or 0. But now we're told that at time 0, you have to get 3 sine 2x minus 6 sine 5x. So what do you think we're going to do? What are we going to do with this u of xt? We're going to plug in t equals 0, and then we're going to match that with what they tell you u of x0 is. That's what we're going to do. So you plug in t equals 0, you get u of x comma 0 equals, well, do you see what's going to happen when you plug in t equals 0 here? That's the only place where you see a t, right? So the exponent's going to be 0, because you have negative 7n squared times 0 is 0. E to the 0 power is 1. So you are just going to get the sum from n equals 1 to infinity of cn sine nx. Okay? Now this, in the problem, they tell you that this is equal to 3 sine 2x minus 6 sine 5x, right? So in general, your u of x0 is going to be some expansion in terms of sine of nx. And in the problem, they tell you it's 3 sine 2x minus 6 sine 5x. So now we set them equal, and then we have to solve for the cn's. So this infinite expansion, let's just make sure we understand what it means. It means that you have an infinite sum, and the sum ranges over all n's. So you're going to get c1 sine 1x, so that's sine x, plus c2 sine 2x, plus c3 sine 3x, and so on, right? So you have this infinite sum, but it's actually equal to 3 sine 2x minus 6 sine 5x. So if you think about it, okay, what is c1 going to be, for instance? c1 is the number being multiplied by sine x. So this 3 sine 2x minus 6 sine 5x, do you see a sine x? No, you don't. So what constant is being multiplied by sine x? 0, right? You have 0 sine x. But what's being multiplied by the sine 2x? 3, right? So your c2 is going to be 3 because that's the constant in front of the sine 2x. And what's c3 equal to? Well, it's going to be 0 because I don't see a sine 3x. And it just goes on like that. So actually, the only non-zero constants are going to be c2 and c5 because I have a sine 2x and a sine 5x. So that tells me that my c2 is going to be 3, my c5 is going to be negative 6, right? Because this is a plus in the summation. So I have a plus negative 6 sine 5x. And then all the other constants all the other CNs are 0. That's what is given by the f of x. And that is what I mean when I said that your f of x is going to tell you what the CNs are. So now that we have the constants, we go back because we're solving for u of xt, right? And now we know what the CNs are. So our u of xt, well, the only non-zero terms that will show up are when n is 2 and n is 5. So you're going to get, so this is when n is 2, the C5 is when n is 5. So I write down what you get when n is 2 and n is 5. So that gives me C2. Actually, I'm just going to write down the general thing and then fill it in. So C2 e to the minus 7 2 squared t sine 2x plus C5 e to the minus 7 times 5 squared t times sine of 5x. And now I plug in the stuff that I have. So I know C2 is 3 e to the, so negative 7 times 2 squared. That's negative 28 t sine 2x. And then plus, well, C5 is negative 6. So I'm going to get minus 6 e to the, and then the exponent turns out to be, so negative 7 times 25 is, put that down somewhere? Yeah, negative 175 t sine 5x. And that's the answer. Let's do one more problem that's similar to this. So solve the heat equation, which is given by equations 1 to 3, meaning these equations I wrote down here. Okay. Solve that equation with beta equals 3, L equals pi, and f of x equals sine x minus 6 sine 4x. So this is pretty much the same as the previous problem, just with different constants. So you take your u of xt, which is, where's my general formula? Here, right? You take this, and then you just substitute beta equals 3 here, and then L equals pi in here, and L equals pi here. And then when you do that, you're going to get u of xt equals the sum from n equals 1 to infinity, cn e to the minus 3n squared t sine nx. And now, remember your f of x is u of x0. So we're going to substitute t equals 0 into that equation and then figure out what you get. So you're going to get the sum from n equals 1 to infinity, cn e to the 0 is 1, cn sine nx. And then you match that with your f of x. So when you match that with your f of x, the only constants that show up, what are the only n's that are relevant here in this infinite sum? So you have a sine x, that's when n equals 1, right? Because sine of 1x. And then this negative 6 sine 4x corresponds to n equals 4, because you get sine of 4x. So you get n equals 1, you get c1 equals what? 1, because you have a 1 times sine x. And then you get n equals 4, and then c4 is equal to negative 6. And then all the other CNs are what? 0. So once we have that, we can use our u of xt equation there. So u of xt equals, so let's write down the n equals 1 term. It's going to be c1, which is 1 times e to the minus 3 times 1 squared, that's 1, t sine 1x, so that's sine x. Okay, that's the n equals 1 term. And then we have the n equals 4 term. So c4 is negative 6, so minus 6 e to the minus 3 times 4 squared t. So 4 squared is 16 times 3 is 48, so negative 48t, and then sine 4x. And that's the answer. So solving these heat flow equations, once you know the formula for the u of xt, is pretty easy as long as your f of x is a sum of sines. Like in this example, in the first example, your f of x was a sum of sine functions, and then you just plug in t equals 0 and then match them. And in the next example, it's the same concept. It's a sum of sine functions. In general, if you have a function, it's not going to be a sum of sine functions. So what if your f of x was like x? And then that leads to the question, can you write x as a sum of sine functions? Well, that's going to lead to something called Fourier series, or Fourier sine series in this case. But there's also Fourier cosine series, and then there's a general Fourier series. So that's the topic we're leading up to. If we knew how to write a function, f of x, as a sum of sines, then we could use the same method that we just used in the previous examples. Okay, so that's that. And then in the next video, I'm going to go over the solution to something called the wave equation, which is a different type of differential equation.